Thanks to our lemma 2a, we not only know that h1 and h2 are continuous, since they are compactly supported on G, we know that they are also uniformly continuous. So let me carefully write this down. The lemma 2a, there exists an open neighborhood V of E. Remember, I use this notation to denote an open neighborhood of an element, such that hi of x minus hi of y has absolute value less than delta for any I equal to 1, 2, whenever y inverse x is in V. This delta is the same delta as in the beginning when we defined this h. This delta is something we said to be specified later. Now we choose V containing the identity element of G such that blah blah blah. Namely, HIs are uniformly continuous. Now for phi in CC plus of G with support of phi containing this V, we choose this phi to be a function in CC plus G with a small support. And I will tell you why we make this choice later. You will see why we make this choice later. By our answer, to the first question after the definition of this Haar covering number with respect to functions. Remember, in our answer to the first question, we explained why this set is non-empty whenever f and phi are in CC plus G. Actually here, phi must be in CC plus G, but f can be 0. Because when f is 0, this triplet holds for any positive C sub j's. So by our answer to that question, namely the set is not empty, there exists constant C1 through Cn greater than 0, and x1 through xn in G such that H, remember how was H defined? H was defined to be F1 plus F2 plus delta times G, which the existence of those constants and those elements gives us that this H is covered or bounded by the following linear combination. And here, we're going to do something that is slightly tricky. Instead of using xj's, we're going to use xj inverses. So if you like, you can put inverses on all of x1 through xg. But this does not change anything essentially. We use xj inverse here just for convenience. You will see why we make this choice. And we give the statement here a label. Let's call this result number 1. We'll use this later. And let us derive the second result, which is a particular case of this. By the uniform continuity, we have hix minus hixj is less than delta whenever xj inverse times x is in support of phi, which is contained in V. This is just a special case of what we did in here. And we'll call this small result number 2. And it follows that if you look at fi of x, this is h of x times hi of x. This is due to the definition for hi of x. Hi of x is defined to be this quotient of fi divided by h. So this is just definition. This guy will be less than or equal to the summation from j equal to 1 to n of c sub j's times phi of x sub j inverse times x times hi of x. We're just copying hi down in here. The first part is just this guy. We're putting this L sub xj inverse inside. This is due to number 1. And now, you can see this part is further less than or equal to. Now we're gonna use the second result here to magnify this to h sub I of xj plus delta. And I tell you this is from here. Now, do you see the subtlety? Can you see this very rigorously? Actually, if you think about this very carefully, there are 2 cases to consider when you want to establish this inequality. There are 2 cases. First, if xj inverse x is not in the support of phi, then the corresponding summand will both be 0. So trivially, this guy will be less than or equal to this. So this is a trivial case. And the non-trivial case is when this xj inverse x is in the support of phi. If this is the case, we are really going to use this second result. We'll take out this absolute value, and hi of x will be less than hi of xj plus delta, as long as this xj inverse x is in the support. This is by number 2. Anyway, we just wrote that this inequality holds for all x in G, and I equal to 1, 2. Now let's continue. What does this tell us? This tells us, together with the definition for fi column phi, So at the last step, I better switch the role of phi and those hs here so that you can see it in a more clear way. This together with the definition for fi column phi. Maybe I should rewrite this further as L sub xj inverse of phi applied to x. This gives us that fi column phi is less than or equal to the summation of all the coefficients. Remember, this quantity was defined as the infimum of all possible such sum of coefficients. And now, let's look at the summation of fi column phi and f2 column phi. The summation f1 column phi plus f2 column phi is less than or equal to the sum of cj's times h1 plus h2 of xj plus 2 delta. There should be 2 delta when you take the sum. And if you simplify this, this gives you sum of cj times 1 plus 2 delta. Why do we have this inequality? This inequality follows from the definition of HIs. H1 plus H2, remember, by definition was F1 plus F2 divided by H, which by definition of H, this is F1 plus F2 divided by F1 plus F2 plus delta times G. And this quantity here is always non-negative, so you get something that is less than or equal to 1. This is how we got this inequality. And this is the result number 3. We'll use this later. That the sum of those two guys is bounded by this quantity. And now, what can you observe from this third result? In particular, I would like to remember the definition for C sub j's. Where did we got C sub j's? What's the meaning of this, especially when you take the sum? So take a look at our construction for C sub j's in here. I guess some of you may have already seen that the summation of C sub j's will always be greater or equal to H column phi, the Haar covering number of H by phi, by our definition at the beginning, by our definition of Haar covering numbers with respect to functions. And furthermore, the number is the infimum of all possible such sum of CJs. So now from number 1 and the definition of H column phi, we can make the summation C sub j's, which is from 1 to n, arbitrarily close to the quantity, this Haar covering number, of H by phi. So the result number 3 is the following inequality, that f1 column phi plus f2 column phi is less than or equal to h column phi times 1 plus 2 delta. This is something we got from 3. This is quite important. We'll give it label number 4. Now we are ready to finish our proof of lemma 2. Remember, in our lemma 2, we want to prove that I sub phi of f1 plus f2 can be as close to the sum of those two things as we want. For any epsilon greater than 0, their difference can be controlled as small as we want, with a careful choice of phi, such that the support is contained in some small neighborhood of the identity. And also recall that we haven't specified how to choose this little delta yet. This is something we want to address in the last stage of our proof. Let's do it. Now, we can finish the proof. Notice that I sub phi of f1 plus I sub phi of f2, by definition, remember they are defined by the quotients. Some of you probably have already forgotten the meaning of f0. But I want to tell you, you don't have to remember the meaning of f0. You only need to know that this is something that is already fixed. Actually, it's fixed even before our statement of lemma 2. This is fixed at the very beginning. We just pick an f0 in CC plus G, and this is how we used to define this I sub phi. So I sub phi actually depends on f0. Anyway, you just treat this as something that is fixed. Don't worry about it. This quantity, by the number 4 result we just derived, is less than or equal to h column phi times 1 plus 2 delta. And we need to divide this guy by f0 column phi. And this is further less than or equal to, let's pull this to the front, and this h column phi is equal to, by definition, f1 plus f2 plus delta column phi divided by f0 column phi. This should be equal. This is just the definition of h. We're just using the definition of h here. But this last quantity is less than or equal to, by our lemma 1 basic properties of Haar covering numbers with respect to functions. We'll break this down into two parts. This is the so-called sub-additivity for the Haar covering numbers with respect to functions. And this guy will be, by definition, again equal to Sv of f1 plus f2 plus delta times Sv of g and we will recombine those terms here into two groups. First, we need to single out a I sub phi of f1 plus f2. Because later we want to compare this with this guy. We want to compare them. And the rest of the term is 2 delta times Sv of f1 plus f2 plus delta times 1 plus 2 delta times I sub v of g. We'll put a bracket around the second part. Maybe you'll give it a star. The star part is equal to and observe that the star part is less than or equal to 2 delta times f1 plus f2 column f naught plus delta times 1 plus 2 delta times g column f naught. Do you see why this is true? I'll let you think about it for a while. This is true because we have the inequality f column phi divided by f naught column phi is less than or equal to f column f naught by lemma 1d, the tower property. So those isophys are, remember, quotients. By tower property, they are less than or equal to the respective Haar covering numbers. And now, do not forget our ultimate goal. Our ultimate goal is to make this part, namely the difference between those sum of those two guys and this, as small as we want. In particular, we want this guy to be less than epsilon. And we haven't chose the delta yet, but now we can do it. Now we can choose delta. How? Now it suffices to choose delta such that this guy to be less than epsilon. We can do this because everything here, f1, f2, f naught, and g, are all independent of our choice of phi. This is really important. We must make sure they are independent of the choice of phi. So now let me write this down, which is independent of phi. So to be less than epsilon. The epsilon we prescribed at the very beginning in the statement of lemma. Once we make this choice of delta, we are done with the proof of the lemma 2. We successfully made the difference of I sub phi of f1 plus f2 and I sub phi of f1 plus I sub phi of f2 as small as we want. And that gives us the additivity of I sub phi in the approximate sense, which is exactly what we want for lemma 2. At this point, let me quickly mention a corollary to lemma 2. If f1 and f2 are in CCG and non-negative, then there exists a sequence of phi sub n's contained in CC plus G such that I sub phi n of f1 plus I sub phi n of f2 minus I sub phi n of f1 plus f2 converges to 0 as n goes to infinity. And now let's prove this corollary. This should be immediately from our lemma 2. So what we do is that for those fixed of f1 and f2, and take epsilon equal to 1 over n in lemma 2, and choose v sub n, an open neighborhood of E, correspondingly, such that this inequality holds for phi equal to some phi sub n whose support is contained in v sub n. So here will be 1 over n, and we are going to replace phis by phi sub n's, where the support of phi sub n is contained in v sub n for any n. Then it follows that the limit of this difference will go to 0 as n go to infinity by this choice. This finishes the proof of this corollary.